Now let us look into another category of frequency representation of signals, that is continuous time Fourier transform. Please note that continuous time Fourier transform is a frequency representation method for continuous time and non-periodic signals. Also please note that by nature the continuous time Fourier transform itself is continuous and non-periodic. Suppose there is a signal x of t which is non-periodic. Its frequency domain representation is given as x of j omega, where x of j omega is equal to integral minus infinity to plus infinity x of t multiplied by e power minus j omega t dt. This is analysis equation. Similarly, the synthesis equation, that is to get x of t from x of j omega, is written as 1 by 2 pi integral minus infinity to plus infinity x of j omega multiplied by e power j omega t dt. Also please note that for a signal x of t, for the continuous time Fourier transform to exist, it has to satisfy the Dirichlet conditions, which are given as below. That is, the signal must be absolutely integrable, that is integral minus infinity to plus infinity mod of x of t dt should be finite, and the signal x of t should have the finite number of maxima and minima in one period. Also, the signal should have the finite number of discontinuities. So, if the given signal satisfies these three conditions, then it means that the signal satisfies Dirichlet condition. So, the continuous time Fourier transform of the given signal x of t exists, and the same is given as integral minus infinity to plus infinity e power minus j omega t dt. And given x of j omega, the equation to get x of t is given as the synthesis equation. Now let us consider an example. Suppose there is a signal x of t which is given as delta of t. Now we have to find the continuous time Fourier transform of x of t, which is given as integral minus infinity to plus infinity x of t e power minus j omega t dt, which upon simplification becomes 1. From this we see that the continuous time Fourier transform of the impulse function is 1, which means that all the frequencies are present in the frequency representation of delta of t, and the magnitude of the same magnitude at all the frequencies is the same. Now let us consider another example, that is x of t is equal to delta of t minus t naught. The continuous time Fourier transform of the same is given as Fourier transform of x of t is equal to integral minus infinity to plus infinity delta of t minus t naught multiplied by e power minus j omega t dt. This is equal to e power minus j omega t naught on simplification. From this we see that magnitude of x of j omega is equal to 1, and phase of x of j omega is equal to minus omega t naught. So similar to delta of t minus t naught also has all the frequencies, and the magnitude at all the frequencies is equal to 1, but the phase at each frequency differs and is a linear plot with respect to omega. Now let us consider another way of frequency domain representation of the signals, that is discrete time Fourier transform. Please note that discrete time Fourier transform is for discrete time and non-periodic signals. Also, by the nature of this DTFT, DTFT is continuous, and periodic. Now let us consider a signal x of n. Its DTFT representation is given as x of e power j omega. So from x of n, the DTFT representation x of e power j omega can be obtained by an analysis equation as sigma n equal to minus infinity to plus infinity x of n e power minus j omega n. So please note that this is analysis equation. Given x of e power j omega, we can get x of n by synthesis equation as 1 by 2 pi integral minus pi to pi x of e power j omega multiplied by e power j omega n d omega. Please note that the equation that we have written now to get x of n from x of e power j omega is synthesis equation. So also the condition for DTFT to exist for a given signal x of n is the signal x of n is absolutely summable. That is integral minus infinity to plus infinity mod of x of n. Sorry, for the given signal x of n, the DTF2 to exist, the given signal x of n should be absolutely summable. That is sigma n equal to minus infinity to plus infinity mod of x of n should be finite. So if this condition is satisfied, then the signal x of n is absolutely summable, then the DTFT of the given signal exists. Now let us consider some of the examples. So we have to find the DTFT of delta of n, which is given as sigma n equal to minus infinity to plus infinity delta of n e power minus j omega n. We know that by the nature of this summation will be finite only for n is equal to 0. So at n is equal to 0, we see that this value is 1. From this, we can say that for a impulse signal, the frequency representation can be given by DTFT, and it is equal to 1 in its frequency domain at all frequencies. Now find the DTFT of delta of del minus n naught, which can be obtained similar to above as e power minus j omega n naught. Now find the Fourier DTFT of 1 by 2 whole power n u of n. We know that 1 by 2 whole power n u of n is 1 by 2 whole power n for n greater than or equal to 0, and it is 0 otherwise. So which upon so the DTFT upon simplification can be written as sigma n equal to 0 to infinity 1 by 2 whole power n e power minus j omega n. So this upon simplification can be written as sigma n equal to 0 to infinity 1 by 2 into e power j omega whole power n. So this upon simplification becomes 1 minus 1 by 2 e power minus j omega. So from this we see that for the given signal, that is 1 by 2 whole power n u of n, which is a causal signal, the DTFT is given as 1 by 1 minus 1 by 2 multiplied by e power minus j omega. So similarly we can prove that given a anti-causal sequence, Fourier transform of minus a power n multiplied by u of minus n minus 1, the frequency representation is given as 1 by 1 minus a into e power minus j omega if mod a is greater than 1. Because if mod a is greater than 1, the signal minus a power n into u of minus n minus 1 is absolutely summable, and the DTFT of the same exists.